dimensions. Newton's constant is effectively the Planck length to the d minus 3, or d minus 2, excuse me. The curvature of ADS space matters. Moreover, there's a the black hole differs from the ADS matrix only in that the blackening factor, it starts out the same way, but then it has a negative term, so that at some radius. Oh, sorry.
Sorry.
Should I repeat all that?
No, it's okay.
Thanks. At some radius, this goes to 0, and there's a horizon. Now, if you work out the, if you work out just from, again, the same dimension analysis, the mass of these three things, it just rises monotonically. That's the mass. But if you work out the temperature, it goes up and then down and then up again. So the going down is the negative specific heat of a black hole in flat space. Here, again, the black hole is in a box much larger than itself, and with black holes, the thing is when they get more massive, their temperature goes down, so they have a negative specific heat. Now, what this means is this has funny thermodynamic behavior. If your system is isolated, so the mass can't change, then every one of these three kinds of black hole is stable, because again the mass is it's monotonically increasing. And if you're doing black hole thought experiments, then you usually would be dealing with an isolated black hole. But it's worth remembering that if you put the system in equilibrium with a bath, then this construction means that the middle phase is unstable, and it will decay to either the 10-dimensional black hole will decay either the gas or the 5-dimensional black hole, or some kind of Maxwell construction. So again, I've got a lot of curves there. Let me label them better. The nice monotonic curve is the mass, and the jagged curve is the temperature, and the dashed line repairs that, repairs that. So at low temperature, the system is in a gas phase in the bulk, and at high temperature, there's a black hole. If you go through the dimension analysis again, you'll find that for the gas phase, the entropy goes as n to the 0. That's the important part, and then T LADS to the 9th. And in the 5D black hole phase, the entropy goes as n squared times T LADS cubed. And again, one of my comments early on about why we believe ADS, one of the many things it gets right is it has the CFT has states that look like black holes, because in fact one expects in the gauge theory, due to the gauge constraint, that at low temperature the gauge constraint forces you to have colorless states, and therefore the entropy should scale should be independent of the size of the gauge group. But past a certain temperature, the density of states kind of overwhelms the constraint. You can see this even at weak coupling in the gauge theory, and there's a transition to a phase in which the entropy goes as n squared, which in the CFT means you're seeing all of the gauge degrees of freedom. And it exactly fits with the scaling in the bulk. So coming back to the main goal here, which is to do thought experiments with black holes, the simplest way to duplicate the thought experiment is to work down in this regime, where the black hole, if you have one, there are smaller black holes, but they have less entropy than the gas, so they will decay to a gas. So the closest analog of the Hawking experiment is to consider these very small black holes, which are unstable. But in fact, you can also, and it's often more useful to think about either of the others. Now, you might say, how can they decay since they're stable? What you can imagine doing in thought experiment land is you have your conformal field theory, which with its dual ADS space, and you're always free to couple a conformal field theory to another quantum field theory, conformal or not. And so there's some kind of bilinear interaction between the two, and that will have the effect that energy can actually flow out of the CFT with the gravity dual into the other one, and it will allow the black hole to decay. From the point of view of the bulk theory, what this means is that instead of the usual reflective boundary conditions, you have some kind of absorptive boundary conditions. And this is kind of, it's nice to consider, it's nice to kind of have the whole catalog of thought experiments that you might do. One thing that's nice about this is, because you can imagine you can control the coupling between the two CFTs, it allows you to do a number of different kinds of thought experiment a number of different kinds of thought experiment. Also, it's kind of nice to work with black holes that are, one of the nice things about ADS CFT is that a black hole is dual to an ordinary thermal system. And now you see the precise statement is that at least at fixed temperature, only above this Hawking-Page transition is the black hole actually the thermal equilibrium state. And so it's nice to work with states that are in thermal equilibrium. And so in any case, any of these will do. You can either have the whole Hawking process happen within the ADS space, or you can have this extra step where the Hawking quanta leak out into another CFT. But in any case, now having set this up, you know, I said this at the beginning of the ADS section. I can just say it again. You just imagine a thought experiment where you in ADS space form a black hole from the vacuum by acting with enough local operators to send in enough energy to make the black hole. You then wait for it to decay. And because these initial and final diffuse states have good CFT duals, you know that this carries pure states to pure states. So it excludes, in whatever theory of quantum gravity, it's pretty much the ugliest black hole ever. It looks like a cockroach. But in whatever theory of gravity is dual to the n equals 4 gauge theory, pure states evolve to pure states. Now, now there were three possibilities, and one possibility is remnants. So remnants, require below some fixed energy, which is not very large, an unbounded number of states. And quantum field theories don't usually have that property. And we kind of, well, this is, so one of the things about this, in the regime where there's a good gravitational description, the gauge theory is strongly coupled, and we can't calculate anything in the gauge theory, but we know a lot about strongly coupled gauge theories, and it's hard to see how it could have a spectrum with that kind of spectrum, with again an unbounded number of states below some finite energy. Our intuition with gauge theories, in fact, matches very much. I think I've already erased that scaling, or maybe the end of the 0 and n squared scaling. But our intuition about gauge, oh, it's there? It's over 0. Why can't I see it? Oh, I'm blind. Okay, good. I'm just blind. Okay, so our intuition about gauge theories is very much consistent with exactly what the gravity dual predicts, and not with the idea that there's an unbounded number of low-energy states, which would mean there was no thermal equilibrium at all. And it's worth remembering, for the point of view, it's worth remembering that and the parameters here, the size of the gauge group and the Tuft parameter, the gauge coupling, are large but fixed. That is, they have to be large enough that this space is larger than the black hole that we're talking about, or the same size, and also, more important, larger than the Planck scale and larger than the string scale. But they don't have to take it to infinity, and that's good, because if we had to take them to infinity to make this argument, then you might say, well, maybe in those limits, some states can sneak, a lot of states could sneak down to low energy, and but that's not an issue here.
Sorry, Joe, but if you want to describe asymptotic flat space black holes, then you don't have to take it.
But I don't want to.
Okay.
Why should I want to? I want a setting where the paradox exists, and the paradox exists in an ADS box that's sufficiently large, about infinite. That's all I mean. Yeah. That's why I don't want to.
So you think the remnant doesn't have anything to do with that? So
if there's no remnants in a box a billion light years across, it's hard to see how there could be a remnants in a box that's infinite. And we don't live in flat space anyway, by the way. But yeah. But no, I mean, this seems like a local problem whose solution is not dependent on yeah. In any case, I would be happy if I could solve it in ADS space. You could keep working on it in other geometries. So before I go on, while we're on the subject of ADS, my next subject is the question: okay, if the information gets out, then how? But before we go on to, there's one more thing I want to do, because it comes up in a lot of discussions with the ADS-CFT duality. So I wrote this dictionary last time, what Harlow and Stanford call the extrapolate dictionary, which is just that the operators in the CFT, I labels the different operators, are the limits of the bulk fields with an appropriate scaling that comes from the conformal symmetry. And now this tells us that if we do some measurement in the CFT, we know what the fields are doing near the boundary. But suppose I give you some state of the CFT that I prepared in some way. And I may have prepared it in such a way that there are gravitons. Let's leave aside black holes for now. Although let's suppose I prepared it in such a way that there are gravitons floating around in the middle of the space. How would I know? How would you know that? How would you look at the state I've given you and know that there are gravitons somewhere in the center of the space, since the dictionary doesn't tell us? And okay, so let's think about how I would have prepared this state. So here's what I would have done is sometime in the past I would have acted with a local operator, and that produces something moving into the bulk. And so the way I would have prepared this state with gravitons somewhere in the center would be by acting with a local operator in the past and letting things propagate. What does this look like in the CFT? So this operator is going to be some gauge invariant thing, something like trace f mu nu. And if you think about what happens when that acts on the vacuum, it kind of creates a couple of photons or gluons, whatever, which will then start to move apart at the speed of light, since it's a conformal field theory. And it's not a free conformal field theory, so they'll interact in various ways. But essentially what will happen is that the longer I wait, meaning the further into the bulk we go, the further away from the boundary, the bigger this excitation will get. And so in order to find gravitons in the bulk, you would be looking for some kind of correlated excitations on top of whatever is present in the vacuum over different length scales. And we can give a more formal version of what I just said. Suppose that so here's again my ADS space, and here's that point. You can't tell. That point's in the bulk, not on the boundary. And what I want to do is I want to construct the field operator at that point. I've got a dictionary for the field operator at the boundary. I want to construct that field operator that field operator in the center. First thing I would do is I would use the Klein-Gordon equation, or whatever is the bulk field equation, to relate the field in the bulk to the field on the boundary in some region. Are there any hands up? Good, I got away with that. Okay, and then once I've used the bulk field equation to relate the field in the center to the field on the boundary, then I can use this dictionary to relate that to an operator in the CFT. So the outcome is that the field at some finite radius is equal to there's some smearing operator. Okay, and then using the dictionary, you get that. So this relates the field in the bulk to some field to the local operator in the boundary, but integrated. And I use the free field equation here, but of course there are interactions, and so the interactions are down. in the 1 over n counting of the field theory, the bulk fields are free fields, so the interactions are of order 1 over n. So there's a systematic 1 over n expansion here. I guess I should put indices here. I, J, K, just for that's not important. Now I'm not quite done because these operators are not, they're smeared over many different times, and I gave you a state at some particular time, but of course we can then use the operator equations of motion to write this, to refer this back to our reference time, which I guess is the time on the left, t. So this would be e to the minus I h t minus t prime, oi of t o prime, e to the I h t. So what this tells you is that there exist in the conformal field theory operators that will answer the question that I asked you. That is, that you can use I give you the state, and you use these operators to find out where the gravitons are in the interior. And this is rather implicit. These smearing operators is just solving the k's are just solving wave equations. Oops, I think I left out some of the arguments here. T prime, theta prime. Yeah, depends on everything in there. These smearing things are just solving wave equations, but this is of evolution in the gauge theory. It's a strongly coupled gauge theory, and so this is an existence proof of the operator, but to actually construct these, you'd have to be able to solve the gauge theory. Actually, there are some kind of fun, you can actually, even in the free gauge theory, there are some fun things you can do with this, like higher spin theory, which is dual to a free theory. You can then do this field. You can actually do this last step explicitly, and you actually get a fairly useful model of holography, even though it's in the extreme weak coupling rather than strong coupling limit. Okay, so that was just the reason I'm saying this is because later on we're going to be talking about physics in the bulk, and we're going to ask how much the conformal field theory knows about it, and so I wanted to kind of give you the existing technology for that problem. By the way, if you actually carry this out, so nobody has yet raised your hand and said, well, yeah, there's even a more basic question. This is not your normal Cauchy problem. I'm integrating in a space-like direction instead of a time-like direction. And it turns out that the problem has not, there is a solution, but actually there are many solutions. The problem is underdetermined. That is, there are many choices for these k's, and the reason is that these O's satisfy dynamical constraints. They largely come from the fact that energies are essentially they come from spectral constraints in the theory, but it means that there are many equivalences. And that's good because the simplest way to find this k is to kind of put phi in the center, use spherical symmetry to reduce it to a 1 plus 1 problem, and 1 plus 1 problem you can switch space and time for free. And that gives you a domain, an integration domain like what I drew here. And then when you pull it back to a single time, it's integrated over that entire slice. But if you were in Mark's lectures, he said that we could reconstruct, let me put the field a little closer to the boundary. So if I put the field a little closer to the boundary, same thing. You still need a whole bunch of, but Mark told you that in fact, to reconstruct this, you only need enough of the state so that when you construct, first of all, in the boundary, its domain of dependence. Oh, wait, I'm not drawing that very well, am I? Oh, right. If you cut in the boundary, it's domain of dependence, and then you construct in the bulk the causal wedge for that. As long as this is in the causal wedge of that, you only need that much of the state. And the ability to reproduce the field from that much of the state instead of the whole thing comes down to, again, the fact that these k's are underdetermined and there are many choices. Now, there's a very interesting paper just out in the last few weeks by Almheri, Dong, and Harlow, which argues that this sort of that this ambiguity, well, which argues that the ability to reconstruct a field. So actually, let me draw this thing from above. So if we draw it from above, here's where let's put the field in the middle. So mark construction would let you reconstruct that field if you know that much of the state, or if you know that much of the state, or if you know, I guess it's that much of the state. And you have, if I've drawn this correctly, you have three sort of regions which have, there is no point that is in all three regions. So it's not clear where is the information about that state. You could act in the boundary with some operator over here, and it can't change the field there because you can reconstruct the field purely from this part of the wave function. Anyway, they relate this to something called quantum secret sharing, which is kind of fun. And I don't know whether, I just think this is interesting. I don't know whether it's deep. Yes?
So for the Rindler wedge, it is known that the k doesn't exist. I mean,
good. Yeah. Good. So thank you. K exists as a function here. Thank you. K exists as a function here only in the larger domain. K exists as a distribution in the Rindler wedge, which means that if I were to write this in momentum space, it exists in momentum space, but not in position space. And however, the operators, it's a distribution, and the operators lie within, they're constrained in such a way that it's a distribution that it makes sense on the operators. So in Fourier space, this thing behaves exponentially in K. So as long as these matrix elements behave, then the whole thing is okay, and that's true. But I still, people keep coming back to this problem in a number of different ways, and it's not clear A, what the best way is to think about it, and B, if anything deep remains. This quantum secret sharing just doesn't see, I mean, I don't know how to relate that to these languages in terms of distributions. Yeah. So this is interesting to think about. Yeah. Let's see.
In the bulk, there's field redefinition ambiguity. So it sounds like.
Oh yeah. There's always that has been. I've made a choice when I've chosen my equation. Yeah. There's also gauge ambiguities, even worse. And so in fact, this has to be the field in some chosen gauge, or the field constructed, sort of defined by some invariant notion of where it is in terms of distances, right?
But of course, when you talk about one-on-one interaction, you're including interaction in the bulk. But so you're saying you specify some interaction for the bulk equation. And
Good. So you're good. So it's interesting. Well, actually, this is so right. So actually, this construction requires that we know the bulk dynamics. The field, we can't just look at the gauge theory and know what no one has figured out how to just look at the gauge theory and figure out what these are. It always involves knowing what the bulk dynamics kind of independently. You would think that maybe space-like commutativity would be enough, but that's by itself it's not enough. Space-like commutativity, but it's interesting. And in fact, there's something I'm going to harp on, and maybe I'll start harping on it right now. I think from many points of view, so in this duality, yes, it was the next item. In this duality, we have a non-perturbative definition of the CFT side, and we have no non-perturbative definition of the bulk theory. What we have is many approximations in different limits, supergravity, string theory, and so the duality has a lot of content. It has a lot of ways it can be checked. But it's a funny thing that there's no non-perturbative construction of the bulk. Again, I mentioned string field theory as an attempt in that direction that hasn't really borne fruit. But I think from many things we learn as we go along about the limits of our ability to understand gravitational physics suggests that we still have to find an independent, non-perturbative description of the bulk.
And for if you're talking about finite NCFT, there's any explanation on how this bulk operator is supposed to obey causality? Say, look at the two-point function and whether
This, yeah.
Of these bulk operator aspects.
Even at finite n, they, well, right. I mean, we know in the strongly coupled theory that, I mean, right. I'm using the language of field theory here, whereas the bulk is ultimately a string theory, and so even here, I'm already assuming that I'm only asking questions at scales above the string scale with these. I mean, right? I don't think anybody's even begun to try to ask the question, in a stringy way. Yeah. The other comment is just, with the black hole information problem, when you have this menu of 3 choices and all of the sub-choices and all of the arguments for and against, at times you wonder, is this worth thinking about, or is there some trivial resolution? And I think that the fact that ADS-CFT was sort of needed to make progress, the fact that we needed this deep new concept is in fact telling us that yes, it was the right thing to think about, and even more because this duality was really discovered from thinking about the black hole information problem after Strominger and Vafa counted states by comparing black brains to D brains. With the information problem in mind, people then started asking what happens if we throw stuff into these or watch them decay. And that's when these coincidences were discovered between very different calculations, which Juan recognized was the hallmark of this new duality. So this is a thought experiment which has really borne fruit. And the question is, have we learned everything from it that we will, or do we have more to learn? And there's certainly a lot more we'd like to know. ADS-CFT is still kind of a black box. I mean, the current state is sort of, I just said that if you evolve in the CFT, you evolve from pure to pure, and we have a dictionary and a lot of evidence that relates these to bulk states. But when we do the calculation in the bulk, we evolve from pure to mixed, and so one of the arrows has a problem. And again, the presumption is that there's something about bulk gravity that we haven't understood, and so when you have 2 calculations that don't agree, you try to break them each into smaller steps. And okay, and so that's what we're going to do in the rest of my lectures. So my next topic is black hole complementarity. So this is a thought experiment largely due to Susskind and Thorlacius and Uglem, but also to Preskel and Tuft, which in some sense argues that so I've been describing the information paradox in terms of this entropy, but it looks at it sort of operationally and asks, is there really a paradox? So here's our black hole horizon. Guess I'll draw it that way. And suppose we start on the outside with 2 bits that are entangled, B1 and B2, and so these are entangled. And we're going to throw B1 in. And it's still entangled with B2. And then according to what we've just learned, eventually the black hole, eventually the state of this bit has to appear in the Hawking radiation. I'll call that B1, I guess, prime. And again, then B2 just propagates along. And so there is there is some, so this is another way of stating the information problem. There is some time here that, that has these 3 bits on it. And again, by what I've just told you, B1 and B2 are entangled. Let's say they're in a pure state together. But also then B1 prime and B2 in a pure state. But B2 is not in a pure state. And so again, we have violated subadditivity. We have violated quantum mechanics. So this is another version of the information problem. Just another way of stating it. But now, what Susskind et al. Ask is, can any observer really see? So these, you might say these are, well, the term is cloned, but the main, what clone here means is that they're entangled. They're both entangled with a 3rd bit in a way that quantum mechanics doesn't allow. Is there any observer who can see both bits? And clearly an observer can't see B1 first and then B1 prime, because once they see B1, they're behind the horizon. But also, provided that the information comes out late enough, then there's no way an observer could see B1 prime and then see B1, because by the time they see B1 prime and jump in, B1 has already hit the singularity. In fact, what you can imagine is an observer waiting in here who measures B1 and sends a signal, kind of the best case. And there's a simple bit of analysis. You know that any signal they send will be redshifted. This is the basic redshifting of the horizon. And so its frequency falls exponentially. In order to send a meaningful signal, you would need to start with very high energy, and because it's exponential, you only really have a logarithmic time. So as long as the delay, let me call this t delay, as long as t delay is greater than order the Schwarzschild radius, which is the basic time, times the log of the black hole mass in Planck units. As long as this is true, then there is no way an observer can see both bits, or in any way receive the consequences of measurements of both bits.
Why it's so? Because it looks like you can draw hypersurface for arbitrary t.
Yes.
You have remnant where you will always have B1 before it can hit singularity.
Ah, you want to wait? Wait. Say again. I can draw. I can draw the surface, yes. But no observer can see. No observer can see both of these before B1 hits the singularity.
Even if B1 hits the singularity or before, any single observer can see all 3 events because there is horizon.
Right. That's right.
But on the other side, you can always draw space like hypersurface.
Yes.
Where you will put everything.
Yes.
Which you will
Yes.
hold inside.
Yes. I agree. I drew it.
Yes.
Yes. So.
But then I don't understand what that means hit singularity.
Pardon? Oh, yeah.
I understand before hit singularity.
Yeah. This.
So you have to synchronize.
This space. So the singularity is up here. Yes. This space-like surface is not hit the singularity. The question is, can any single observer, not the space-like slice, that's not an observer, can any single observer see both? And the conclusion is that this is a rather weak condition, because remember, the lifetime of the black hole, if we're in 4 dimensions, is actually in Planck units. This is the mass. So this is m log. In Planck units, this is m log m. But the lifetime of the black hole is m cubed. So this is a tiny fraction of the life of the black hole. As long as it just takes a little while for the duplicated bit to come out, there is no operational contradiction. And that seems like a very deep statement, because we know that in getting to general relativity and in special relativity and quantum mechanics, it was very important to think about. What was operationally measurable. But if that's the loophole, it really is radical, because in gravity regarded as in gravity canonically quantized, or even quantized in a path integral, the state on such a space-like surface is a meaningful thing. It's part of the theory. And when you go to string theory, where you've got extra heavy stuff that you integrate out, again, you still expect that when you integrate things out, the basic framework where the state on a space like slice is something that is described in the theory, and the state on that slice has to satisfy the usual rules of quantum mechanics. If black hole complementarity is saying that one has to give that up, that the basic framework of quantum gravity is very different. It's not a tiny bit different. It's very different from what you would get by canonically quantizing Einstein gravity. Okay. Now, having said that, by the way, this time is known as the scrambling time now. And I won't say much about the scrambling time except to say that there's some evidence that it's an interesting time. It's kind of the time over which the black hole gets massively mixed up. And also, according to Hayden and Press, pardon?
Did you derive this?
I did. So this I had told you how it was derived by. I said that any signal will redshift exponentially, and so the time over which you can possibly send it can only be logarithmic. Yeah. This is the time scale for black holes, and this is the large number that would come in. Yeah. This is the amount of redshifting you could stand. I mean, you can. Yeah, I think that's all. I mean, you can go back to the original paper by Susskind for a more detailed geometric argument, but again, and you fire a laser, and after a while the wavelength is
inside the horizon or outside.
Well, it has to be inside because
inside.
You have to measure B1 behind the horizon, so you have to do it inside. But you want to do it as close to the horizon as possible because the further you get inside, the sooner the horizon meets you. So right behind the horizon, you measure B1, send a signal as parallel to the horizon as you can, but by this time, it will have fallen into the singularity because of the redshifting. Yeah. Now,
There should be some cutoff there related to the cutoff of the distance from the horizon.
well, I assumed the best case, which is that you fired at a Planck length behind the horizon. I mean, there's a, yeah. All of the assumptions go in the log. So if you change the argument of the log by by squaring it, it's only a factor of 2 in the front. So yeah. Now the question is what this means. So the question is what this means, and because it seemed right to me, but in trying to make precise what it means. So just from your recall, with the uncertainty principle, there's some distance from the uncertainty principle to the idea of wave functions and the Born rule. And so the question is, what is this? If this is the point, what is it telling us? And so I just want to give you a couple of possible things that it might mean. So I think a common interpretation of this, you talk to Lenny now, and it's not clear. But a common interpretation of this is what I want to call it global complementarity, which says that there is some global Hilbert space, some global set of space. There is one Hilbert space. But operators don't commute at space-like separation. I think this was the common interpretation. That is, here's your space, and normally you would have operators. You would have an operator that creates the bit B1. You would have an operator that creates the bit B1 prime. they would be independent operators. They would commute. You could act with one but not the other. And so there'd be, there's a basic framework of locality here. And so the idea, one interpretation, which was I think the broadest one, is that no, that there's this operator and there's this operator, but in fact they don't commute because this one is acting in the same Hilbert space as this one, but in some very scrambled way. And actually, I think this is morally, so ADS-CFT, as I'll go on to say, doesn't tell us a lot about what the answer is, but I feel like this is morally very similar to the lesson of ADS-CFT, because with ADS-CFT, we can talk about operators in the bulk, we can talk about operators in the boundary, so they're seemingly at space-like separation with respect to each other, but they don't commute. And in fact, all the information that's present in the bulk is present in the CFT. And so this interpretation of that thought experiment seems very plausible, and especially in the light of it. This came a few years before ADS-CFT, but and then ADS-CFT seemed as like a realization of this idea. Recently, this term global complementarity is new, but we need it because there's another notion of strong complementarity, which says that each observer has their own wave function. Has their own Hilbert space. So this is very different. In fact, this is already kind of this is nice from the point of view of quantum mechanics. You have a single Hilbert space. This is already a weakening of quantum mechanics because it means that the Hilbert space structure is somehow subordinate to the causal structure. The most developed ideas along these lines are by Banks and Fischler, but it's not really clear what it means. And even there, they have to sort of impose from the start. It's not clear what that would mean, but it seems like certainly a weakening of our notion of quantum mechanics. Now, when they each have their own Hilbert space, there have to be some, of course, when they can both measure the same thing, there has to be some kind of matching condition.
You mean each observer inside, one outside, one inside?
Well,
even in Minkowski space.
Even in Minkowski, it's not such an issue, but say I mean, these questions come up in cosmology too. The question is, what is the right setting for quantum gravity in the context of cosmology? And it's natural I mean, I would say it's still natural to think that there is some single Hilbert space. Well,
Within horizon.
well, no, the question, is there a single Hilbert space that describes the entire, universe, multiverse, whatever, or does each observer have their own Hilbert space, which are not contained within each other, not contained within any global construction, but where there are some matching conditions when they can see the same thing. And then a third thing, which yes.
So in the context of global complementarity, once you give up that local operators commute as space-like separation, is it even clear how to define local operators, since you can wavelength smear some operator, isn't that just equally as good?
Yeah, I mean, well, yeah, I mean, I gave you a construction for the context of ADS-CFT, which was not very wonderful. I mean, it works, but it's not very wonderful. You'd want something more intrinsic, I think. And I don't know anything better than that, though. Yeah. Sorry. Oh. And the last thing I'll mention is what I'm going to call nonlinear complementarity. Which I'll explain what I mean by that in the next lecture. But it's a subset of these. Maybe it could be this or this, but with the additional complication that the operators aren't linear operators. So it's yet an additional modification of quantum mechanics. Okay, so this thought experiment here was so black hole complementarity is again the statement that there's not a contradiction if you stick to things that are operationally measurable. And so this was enshrined as a set of postulates. The first one was purity. The process matter to black hole to Hawking radiation is described by a unitary S matrix. Two is that the observations outside the black hole are described by quantum field theory in curved space-time, or as I prefer to say it, by gravity as an effective field theory. There's a third postulate, which we don't really need, but it's that the Bekenstein-Hawking entropy has a statistical interpretation. It counts states. So let me just say it that way: e to the s bh counts states. And then the fourth is that an observer who falls through the horizon also sees nothing outside. You could say, again, all their physics is accounted for by the effective field theory of gravity. So an observer, so we call no drama. This is effective field, so no drama. Observations of an infalling observer are also described by effective field theory. Okay, so these are so important, I'll draw a frame around them.
Joe, when you say unity as matrix, is it unity evolution, or you just care about
there?
Minus infinity plus.
You see, Lenny Susskind spoke to a burning black hole, and this is what he brought back. So.
But this is not the faith-based.
Anyway, so was there a question? Sorry.
I was asking whether unitary S matrix means unitary evolution throughout. That's what you mean.
S matrix means the relation between the initial state and the final state. So
Okay.
it doesn't speak to what's happening in the middle.
Okay.
Yeah. Okay. I hope this isn't offensive. No. Okay. Good. So in this thought experiment, in these postulates, it's useful to keep some models in mind. So first, a simple one. I think again one of the takeaways that one of the sort of images that went with this idea is that as seen from the outside. Here's your horizon now. I'll draw it in some coordinate, Eddington-Finkelstein coordinates, which we saw earlier today, where it's vertical. As seen from the outside, the horizon looks like a dynamical membrane. And the membrane you can put a little ways outside the horizon. And this fits actually, it's known already in classical general relativity, the membrane paradigm, the black hole behaves as though sitting just outside the horizon. There's a surface with a definite conductivity and diffusion constant and so on. And so the idea is it's seen from the outside, this membrane absorbs anything thrown in. holds onto it, processes it in some complex, non-perturbative way, and eventually spits it out. So that's it in particular. That when I think about assumption 2 here, it's the idea that from the outside, all of the interesting dynamics is happening in this membrane, and then once we go outside the membrane, then we could just use ordinary physics. And then assumption 4 is that, okay, that's what that observer sees, whereas the observer who falls in through some magic of duality doesn't see a membrane at all. Okay, now the recent interest comes about because these assumptions are seemingly mutually inconsistent. And it's really, I mean, no-go theorems are kind of, you know, you can, it's better, what's really better than a no-go theorem is you try to make a model. And if you fail enough times to make a model, then you try to prove a no-go theorem. So we make a model, and we see why the model doesn't work. Then we, then we can understand even better why these postulates are inconsistent. So the model is this. I want to model the state of the black hole and the Hawking radiation. This kind of model, by the way, comes from Samir Mathur, bit model, and also has been developed by his various students and postdocs and by Steve Giddings. So I'm going to have, how do I want to number these? B hat 1, B hat 2, dot, 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 B hat n, put a bar there, Bn, Bn minus 1, dot, 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 B1. And so you can think of these as just bits on a line. You can think of them as spins, each of which can have 2 values for simplicity, just up or down or 0 or 1. Good. And the hat, which I've kind of made it redundant, both the hat and the bar tell you these are inside the black hole and these are outside the black hole. And so the Hawking process would say that at each time step, at each sort of light crossing time of the black hole, you insert another pair of bits right in the middle. Okay, so you have one more, you've inserted 2 bits. You have one more bit on the outside, the additional Hawking particle. You have one more bit on the inside, because as we've seen, this is describing the state on a nice slice. The whole nice slice is getting longer. So this is a cartoon of the Hawking process. And it comes with the usual problems, namely, by the end of the evolution, we have this enormous string of bits inside entangled with an equally enormous string of bits outside, and what happens next, remnants or information loss. Now, let's try to make a model that instead it doesn't lose information. So here's an example of such a model. We're going to take these 2 bits here, and we're going to do the following. We're going to just delete them. So we start at B3, B4, dot, 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 B hat n. And then we're going to insert here, in the middle, one on the inside and one on the outside, that pair. And then go on what was already there. Okay, so we'll take these and we'll insert. Now we're good. Now we're good because the inside, instead of getting 1 unit longer, the inside has gotten 1 unit shorter because we took 2 away, which is what it has to do as the black hole decays. And in this case, the bit that we emitted is entangled with one of the inside bits. In this case, the bit that we just emitted, in this simple model example, is entangled with one of the earlier Hawking bits. So this does what we want. It gets the information out, and eventually you have nothing left inside and the outside in a pure state. Pardon? Because remember, these were each of these bits was produced by the same process. B1 and B1, thank you for asking, I should be clear. B1 and B1 hat are the first Hawking pair, B2 and B2 hat are the second Hawking pair. And so if getting to, yeah, that's good, thanks. Now this is an oversimple model because it's not going to happen that the Hawking bits are paired are entangled in some simple pairwise way. So to make a more realistic model, you would maybe also include some kind of unitary transformation on the inside. You would produce some kind of unitary transformation on the inside, and so the things would be more scrambled, but it's the same idea. Good. Question?
Is this model consistent with the adiabatic principle at the horizon?
No, it's not. No, it's not. So right, so that we've done something. We've changed the physics at the horizon at order 1. Now, so far at least, though, this model doesn't incorporate complementarity because it refers to the state on the entire slice. Unfortunately, so you might think, okay, I'm going to make a model of black hole complementarity by some kind of bit model that either fits in the framework of strong complementarity or global complementarity, and it very quickly doesn't work. And the reason it doesn't work is basically because of Mathur's subadditivity argument. Namely, in order to get a contradiction, we don't need the whole string of bits. We only need to look at sort of the last bit, the first bit inside, the first bit outside, and all the earlier bits outside. And already we have a contradiction because, again, these have to be entangled by the assumption of purity, and these have to be entangled by the assumption that effective field theory works for the inflowing observer. And so, complementarity actually buys you nothing here. And so, in fact, so Mathur states this as a theorem, and that if the information comes out, then the predictions of quantum field theory and curved space-time have to change in the region of the horizon at order 1. Okay, really, this is so close to the firewall that, but the thing is with this bit model, because everything is kind of smeared out over the Schwarzschild radius, it doesn't really localize the problem. Fortunately, the postulates here are phrased in such a way that we can localize the problem somewhat further. And so now, thinking about everything I said, there's not much more to say about why there's an inconsistency. Again, purity requires that B and E are entangled. No drama, that is affect quantum field theory and curved space-time working in the region of the horizon implies that B and B hat are entangled. The third assumption here about the statistical interpretation doesn't really play a role. The second assumption is used implicitly because this is the mode B as it's seen by the observer outside at infinity. This is the mode B as it's seen by an observer who crosses the horizon. And so assumption 2 here, the assumption about effective field theory outside, is used only in a very weak order 1 way, that the free propagation of the bit B from the near horizon region to the asymptotic region is described to order 1 by effective field theory. So that's the contradiction. Yes?
The bit model relies, the key assumption here is that the Hawking process at far separate times have nothing to do with each other.
That's right.
And that, so you say that follows from the assumption of the validity of effective field theory. But,
Yes.
So you are strictly forbidden, say, tiny corrections that grossly violate the value.
tiny corrections that grossly violate. So yeah, I guess I'm at this level. I am doing what you said. But again, I want to emphasize, for example, this assumption is really used at only an order 1 level. I think so. You should be thinking about ways to try to avoid these. And when I describe to you how we would, so what I want to do in my remaining 7 minutes is to talk briefly about the consequences of giving up each of these, and then next time I'll talk more about models by which you might do that. So if you again, the first assumption assumes again that the Hawking radiation, as stated by the Bush, by Susskind, it assumes that that the Hawking radiation carries the information. So either and where this comes in again is that in that case on the page curve, there is a long period where an entropy is going down. With either remnants or information loss, that doesn't happen. The entropy continues to go up following the Hawking curve, and so you don't get the contradiction. So if either remnants or information loss would evade this paradox. So that would be giving up assumption 1. Again, assumption 2, as I've already said, uses effective field theory at an order 1 level. And I'll talk next time about a model, what a model would look like that didn't satisfy that. Assumption 3, we don't really use, assumption 3 more or less follows from assumption 1 because assumption 3 says that because of 1, the curve has to come down. So it more or less says that the fine-grained entropy can't exceed the coarse-grained entropy. And so 1, to a large extent, implies 3. And actually, with 4, with no drama, there are 2 ways that you might imagine it being violated. There's what I'll call fiery drama and quantum drama. How do you spell fiery? Fiery drama and quantum drama. So fiery drama. So if B and B hat are not entangled, then A does not annihilate the state of the black hole, and this is the particle destruction operator as interpreted by an infalling observer. So it's saying there are particles there. How energetic? Again, drawing my horizon Eddington's way so I can emphasize this. As you follow these modes further back, they get closer and closer to the horizon. They become more and more blue shifted. So in effective field theory, there's really no upper limit how energetic that can be. Simply the energy is the limit on whatever, the energy just comes from the point where you stop believing effective field theory. So how energetic? Basically the cutoff. And how many? And here's an interesting question. Because this contradiction I've been talking about, so there's this mismatch between the plus and minus, the relative purity and no drama require that these entropy curves go up or down by the amount of entanglement, by the von Neumann entropy of S sub B at each step. But there are these gray body factors. And as you go to larger and larger angular momenta, they grow exponentially. And so you don't need L to be very large before this is so small, this discrepancy is so small that you can imagine a small effect doing away with it. So if you take this argument and assume the best case scenario that things are only as bad as they have to be then you would get what we call an S-wave firewall. How many? So one possibility is an S-wave firewall. Now, that doesn't seem as so the fact that the infalling observer has a chance to see one of these particles doesn't seem as dramatic as the prospect that they would necessarily see many of them. But it still is dramatic that there are particles that exist with no right to exist. So this is already something that needs a theory. I won't go through this, but there's a classic set of arguments in general relativity involving mining experiments where you basically drop down an apparatus and then pull it out again. And you can defeat the centrifugal barrier in this way because you can lower it by hand and pull it out. And if you believe that these mining experiments make sense and you can use them in the same way, it would be all partial waves. In which case, it basically means everywhere along the horizon. You know, if this is going to happen, it may as well happen all the way. All partial waves are excited. So these are kind of two extreme possibilities. A third question is when it forms, but I'll save that. And the last thing I want to say is, what do I mean by, when? Okay, the last thing I want to say is, what do I mean by quantum drama? What do I mean by quantum drama? So, okay, so our observer jumps into the black hole, and they capture 3 bits. The bit from the early radiation, they capture it. The bit on the outside they capture, and the bit on the inside they capture. And again, there's one principle that says that these two are entangled, and one principle that says that these two are entangled. Suppose that both things are true. If they measure this entanglement, they find that it's there. If they measure this entanglement, they find that it's there. Now, again, that's quantum drama, because quantum mechanics doesn't allow that. It's sort of like, to bring that, it's sort of like saying, imagine I have a spin a half, and I prepare it in a state s sub z equals plus a half. You know that if you measure s sub x, s sub x, then you have 50-50 to find either answer. Suppose I tell you I've got a bunch of spins, and I prepared each of them such that if you measure s sub z, you get plus a half. And if you measure s sub x, you get plus a half. And you take these spins and you start measuring x and z at random, and you find this. That's a lot spookier than just burning up at the horizon, because that says that there is something very basic about quantum physics that we have to change. And even if we're jumping through a black hole horizon while we do these measurements, this still shouldn't happen. So what I want to do, again, next time I said the last thing I really have to do is to describe models of these different things. And I will describe you a model in which this is what happens. There are also other kinds of quantum drama in which different things happen. So I'll stop there and continue next time. Thank you.
Okay, thank you very much, and we'll resume in 15 minutes.